This is our last video dealing with all of the different types of force situations that we have that can cause accelerations on objects. I want to start with this one. This was the one that we just finished on an inclined plane without friction. If you haven't watched that, you might want to go back and take a quick peek, because I'm going to start with the same sort of scenario here. I'm just going to add in friction this time. So we'll know there's friction if I give you a mu number. We'll assume that this one has not started moving yet. That means that there's a static friction on it, and we'll make it 0.5. So with that, I want to know, will this object accelerate? It depends upon, since I'm assuming it's not moving to begin with, that would be stated in the problem. So we have a box at rest. Here's all the numbers. Will the box accelerate? And if so, what's the acceleration number? If the force of friction is large enough, in this case, now we have the force of friction going up the hill. We have this F plane, which is the force trying to pull it down the plane, which once again, out of the law of sines, we get mg sine theta out of this math. I guess I did not necessarily point that out. This is mg, right? This is the sine of theta, and that's where the mg sine theta comes from. If that is smaller than the force of friction, the box will not even move. If the box is already moving and FF is bigger than this, it's going to make the box decrease in velocity. So to start with, we had the F plane of 14 newtons. That is not going to change even though we have a force of friction on it. The only thing the F plane depends upon is the angle, right, and the force of gravity here. If we change either of those, it's going to change F plane. Adding on friction is not going to change that at all. So actually, I think I'll just leave this all hang up here. What's going to change is our acceleration. So we had this last time. I'm going to go ahead and cancel that out, right, which is going to, oh, I guess this is still the same. Our mass of the object is 2.86 kilograms. We might need that. What we are going to change, though, is our net force equation, because now our F net is going to be, right, F plane minus the force of friction, right? You have to assume that it's going to accelerate in one direction or the other. So let's start by assuming that it's going to go this way. And if we get a positive number then for our F net, that will be true. If we get a negative number, it means the force of friction is larger. And so I said, since I said it's static friction, it's not going to then move at all. If it's not moving already, or if it is moving, then this would actually have to be changed to a kinetic friction number, which would probably end up being about the same thing, and then the object would actually just be slowing down, coming down the hill. So once again, F net, we don't know what that is. That's going to be the mass of the object, though, which, yep, this is 2.86 kilograms, times the acceleration is going to be 14 newtons, which is the F plane minus the force of friction, which is mu, there we go, mu times the Fn side, I should put this one, the Fn side of that inclined plane, magic triangle, right? We need this inclined plane magic triangle to figure out what's going on, because once again, this time the force of gravity pulling down is not exactly equal to the normal force. The normal force is the other side of that triangle. So force of friction is mu times the normal force. Right, so we need to actually calculate that. So it's another quick law of sines. Once again, with SOHCAHTOA stuff, it would be mg cosine theta, but since we've used law of sines and everything else, I think I'm going to use law of sines for this one too. Tell you what, I'm just going to do that math over here since we have room. So it's again 28 newtons over the sine of 90 degrees is going to be Fn over the sine of 60 degrees. Fn is across from this bottom angle, and if the top angle is 30, so I should move my hand 30, this angle is going to be 60. So Fn is across from the 60. So if we do this algebra with the trigonometry, we're going to cross multiply Fn times sine of 90, which is 1, right? Fn times 1 is 28 times the sine of 60. So I'm going to go 28 times the sine of 60, and I get 24.2. So Fn is 24.2 newtons. So this equals 14 minus 0.5 times 24.2. This is 24.2. And I'm just going to kind of do the math all at once here. It's 12.1. And then we do our math, we get 1.9 is the net force, which is 2.86 times the acceleration So then if we do our math, the acceleration is 1.9 divided by 2.86 equals 0.66 meters per second squared. Significantly less than it was before. Right before it was half the acceleration of gravity. That friction has significantly decreased the acceleration of the object. So there we go, that's the acceleration. Once again, if we want to find the actual net force, we take it times the mass of the object, and yeah, we get that 1.9, right? So the net force is 1.9 newtons. Right? Before, the net force on the object was 14 newtons, which was the F plane. So there we go. That's how we solve one of these with friction. And once again, it's not incredibly complicated as long as you can get that magic triangle and find the sides of it. The bottom F plane is always going to be, doing the law of sines, or once again, you can use SOHCAHTOA if you want to, whichever you're comfortable with. That will give you the plane force, which is the force pulling it downhill. The other side of that triangle, which once again, once you find one side of the triangle, you can always also use Pythagorean theorem to find the other side. That's perfectly acceptable too. Once again, you might be off by a sig figure 2, so these numbers may be off slightly. Again, as long as you set it up and do the math correctly, you will be fine. So this is an inclined plane with friction. Thanks for watching.